cs407 Numerical Analysis, Section 4.2 Errors in Polynomial Interpolation. This is going to be somewhat of a shorter section than what we had last time with the 20 pages of interpolation. So, interpolation, if you'll recall from last time, produces a function where you have zero error, at least theoretically. You may get machine numbers or rounding at each node of interpolation. So the expectation is that as you put more nodes in, the agreement between the interpolation and the actual values is going to get better. Unfortunately, this is not the case, and you probably shouldn't be shocked to find this out after the lab assignment in the previous 3 chapters. Once again, we'll turn to an example to see how the numbers will, in your words, lie to us. So, consider this table here. We have x takes on the values 0, 1, 3, 4, and 8 as nodes. And at 0 will take on 8, at 1 will take on 12, at 3 will take on 2, at 4 will take on 6, and at 8 will take on 0. So we can construct and plot the interpolation polynomial using the 2 outermost points, so the 0, 8 and the 8, 0. And that's just going to give us a straight line between those 2 points. Then what we'll do is we'll add in the points 3, 2, 4, 6, 1, 12 in that order, and plot a curve for each additional point. You can see these curves F2, F3, and F4 over on the graph to the right. What we end up getting with those curves is as the number of points go up, instead of a smooth curve that goes through all the points, as we have more points, the approximation to the actual data gets worse and worse instead of better and better. The reason is that we're getting higher degree polynomials. Polynomial degree n is going to have n zeros. If all these zeros are real, then the curve is going to cross the x-axis n times. And that means the curve ends up making a lot of turns. We're going to see an improved method for handling this when we get to splines in Chapter 6. But what we're interested in now is how bad things can get. In order to do that, let's take a look at another pathological example that'll help further motivate us. And this one is called the Dirichlet function. So the Dirichlet function takes on 1 at each irrational point. Things like pi, square root of 2, it'll take on a value of 1. And it'll take on 0 at each rational point. So if we put in 1, it'll give us a 0. Now, if we choose nodes that are rational numbers, then p of x is equal to 0. And f of x minus p of x, the polynomial interpolant, is going to be 0 for all the rational values, and 1 for all the irrational values. Now, if you're looking at this, it's clearly not a well-behaved function. Even if it is well-behaved, we can't assume that the differences between f of x and p of x are small when the number of interpolating nodes is large. So even for well-behaved functions that possess continuous derivatives of all orders on the interval, we can't assume that the interpolation is going to work at higher orders. Let's take a look at another example called the range function. So the range function is defined as f of x is equal to 1 plus x squared to the minus 1. So it's 1 over 1 plus x squared. And it takes place on the interval minus 5 to 5. We're going to let p sub n be the polynomial that interpolates this function at n plus 1 equally spaced points on that interval, including the endpoints. Now, as we have more and more points, it's going to increase the error at the non-modal points. In other words, points where we're not adding at the non-nodal points, the non-nodes. And the error is going to actually increase beyond all bounds due to the fact that as we take the limit as n goes to infinity over the interval minus 5 to 5 of f of x minus p n of x, and we look at the maximum one, it's actually going to go to infinity. So, as Buzz Lightyear would say, to infinity and beyond. The moral of this example is that polynomial interpolation of high degree with the law of nodes is a risky operation, and the resulting polynomials can be pretty unsatisfactory as representations of functions, unless you spend a good deal of time selecting the right nodes to interpolate. Oddly enough, one of the problems occurs due to equally spaced nodes. And again, that's kind of contrary to our intuition. So we would think that equally spaced nodes are usually a good choice for interpolation, but they're usually a pretty bad choice. A much better choice for the n+1 nodes in the interval -1 to 1 are the Chebyshev nodes, again the guy from chapter 1.1. And the Chebyshev nodes are x sub I is equal to the cosine of 2i plus 1 divided by 2n plus 2 times pi. And over the interval AB, we can extend these out to any arbitrary interval AB with the formula in the third bullet point down here. Notice these nodes are numbered right to left. Since the theory doesn't depend on any particular ordering, this isn't going to be a problem for us. Let's take a look at an illustrative example to see some of the power behind these Chebyshev nodes. So again, consider our poorly behaved function, the range function. F of x is 1 over 1 plus x squared on the interval -5 to 5. If we select the 9 equally spaced nodes on this graph and plot them, we get the following graph. So you can see the resulting curve assumes negative values, which is something the range function doesn't have. You can see the negative values here and here. Adding more equally spaced nodes and making a higher degree polynomial would even make things worse. Now, when the 9 Chebyshev nodes are used, the resulting polynomial curve is smoother. The Chebyshev nodes of T9 are obtained by taking equally spaced points on the unit circle and projecting them onto the horizontal axis. We're going to get even better results when we use the spline functions in chapter 6. So a couple of theorems on the errors that we can expect with interpolation. The first one, if P is a polynomial of degree at most n that interpolates f at n+1 distinct nodes, x0, x1 to xn, belonging to an interval AB, and if the n plus first derivative of f is continuous, then for each x in AB, there is a xi in AB, for which f of x minus p of x is equal to 1 divided by n+1 factorial times the n plus first derivative of f of xi, and we multiply that by x minus x sub I. So this shows it's possible to assess the errors of interpolation by means of a formula that involves the n plus first derivative. And the proof of this theorem actually relies on something called Roles Theorem, which is if you have x that's continuous on AB, the closed interval, and differentiable on the open interval of AB, if f of A is equal to f of B is equal to 0, then we can conclude f prime of C is equal to 0 at some point C in the open interval AB. And there's a related lemma called the upper bound lemma, no relation to upward bound. And basically it says if x sub I is equal to a plus I sub h for I equals 0 through n, and that h, and that's our interval, is equal to b minus a divided by n, then for any x in that interval, there is actually going to be a bound on the error that we will encounter with interpolation. And that's the special case that arises when the nodes are equally spaced. Now let's look at a second interpolation error theorem. So we can now find a bound on the interpolation error. The theorem gives the bound on the error we can expect from an interpolating polynomial at n+1 spaced nodes. And basically, by any other means, we can actually use other means to find tighter upper bounds for small values of n. If the nodes are not uniformly spaced, then a better bound can be found using the use of Chebyshev nodes. So again, this one gives us an upper bound in terms of the error when we have the equally spaced nodes. Let's take a look at an example to illustrate things. So assume sine of x is replaced by an interpolation polynomial that has 10 equally spaced nodes in the interval 0 to 1.6875 like we did in the lab. So So we can use the second interpolation error theorem, and we have f of x is sine of x, n is equal to 9, because n plus 1 is 10, a is 0, b is 1.6875, and we can let m equal 1. The result tells us that the absolute value of sine of x minus the interpolating polynomial p of x is going to be less than 1.34 times 10 to the minus 9th. So p of x is going to represent sine x on the interval with an error of at most 2 units in the 9th decimal place. So therefore the interpolation polynomial that has 10 equally spaced nodes on 0 to 1.6875 approximates sine of x to at least 8 decimal digits of accuracy. In fact, a careful check on a computer usually reveals that the polynomial is accurate to even more decimal places. So let's take a look at the final third and fourth interpolation error theorems. So the error expression in the polynomial interpolates can be given in terms of divided differences, and that's what the third interpolation error theorem says. If p is a polynomial of degree n that interpolates the function f at nodes x0, x1 through xn, then for any x that is not a node, f of x minus p of x is equal to the divided differences times the product of x minus x of I. Theorem 4 shows that there's a relationship between the divided differences and the derivatives, in particular the nth derivative. And as an immediate consequence of this theorem, we can observe that all higher order divided differences are 0 for a polynomial. And that's what the corollary says, which is actually the important part here. If f is a polynomial of degree n, then all the divided differences, f of x0, x1, x sub I, are 0 for I is greater than n plus 1. Let's take a look at an example of how this can actually help us out. So we can start with, is there a cubic polynomial that takes on the following table of values? Well, start with a solution, and we remember the solution from section 4.1. So the corollary on the previous slide tells us if such a polynomial exists, its fourth order divided differences would all be 0. So what can we do? We can use the techniques from section 4.1 to build the table in C. And the author supplies the table but doesn't work through all the particular details that he did in section 4.1. But here's the table. Now what we can notice is that the fourth order divided differences are all 0. And since they're all 0, then there's a polynomial of degree 3 that fits all the data points in this table. And in particular, we can use the divided differences table to get that as minus 2 plus 18 times x minus 1 minus 9 times x plus 2 times x minus 1 plus 2 times x plus 2, x minus 1, x. So again, in the text they don't work this out in exquisite detail, but you should know how to do this from 4.1 already. So next time we'll take a look at how to estimate derivatives and do Richardson extrapolation. This will be a fairly medium length section before we head into the topic of numerical integration.